At 7:37 in the morning Philippine time on June 8, 2026, one of the most powerful earthquakes ever recorded in the modern history of the southern Philippines struck beneath the waters southwest of Kablalan in Sarangani. Within less than a minute, an enormous section of the Earth's crust shifted, releasing energy accumulated through decades of tectonic motion. When the shaking stopped, the region was not merely damaged. It had been physically reshaped. Along portions of the southern Mindanao coastline, land that had once sat at sea level was suddenly raised by as much as approximately 6.5 feet, or about 2 meters. Areas that had been underwater only moments before became dry ground. Reefs emerged into the sunlight. Shallow coastal waters retreated. In some locations, residents looked toward familiar shorelines and discovered that the sea itself appeared to have vanished. The earthquake was officially measured at magnitude 7.8 and occurred approximately 16 miles, or 26 kilometers, southwest of Kablalan. Its hypocenter was located about 34 miles beneath the surface, equivalent to roughly 55 kilometers in depth. Scientific analyses indicated that the event resulted from thrust faulting within the complex tectonic environment surrounding southern Mindanao, where major plates converge and interact. The earthquake represented a sudden release of stress associated with the ongoing westward subduction of the Philippine Sea Plate beneath neighboring tectonic blocks. Although the shaking itself lasted less than a minute, the geological consequences may remain visible for generations. The southern Philippines occupies one of the most tectonically active regions on Earth. Far from being a single simple plate boundary, the region contains a mosaic of interacting microplates, trenches, faults, and deforming crustal blocks. The motion occurring beneath Mindanao is part of a larger process that has been shaping Southeast Asia for millions of years. Every year, the Philippine Sea Plate moves several inches toward neighboring plates. The rate may seem insignificant when measured annually, but tectonic stress accumulates continuously. Rocks along plate boundaries deform slowly as enormous forces build beneath the surface. For years, decades, or even centuries, these rocks remain locked together despite the pressure. Eventually, the accumulated stress exceeds the strength of the fault. When that threshold is crossed, the crust ruptures. That rupture is an earthquake. In this case, the fault movement was not primarily horizontal. Instead, it involved vertical displacement. The moment tensor solution released after the earthquake revealed rake values close to 90 degrees, a classic signature of reverse or thrust faulting. The fault motion essentially forced one block of crust upward relative to another. Because the event occurred within a subduction environment, the overriding plate experienced rapid uplift during the rupture process. The seismic data indicated a remarkably clean tectonic event, with a very high double couple percentage, meaning that the earthquake closely matched the expected behavior of a major tectonic thrust rupture. That detail is crucial because it explains why entire sections of coastline rose almost instantaneously. Many people think of earthquakes as events that merely shake the ground. In reality, the most powerful earthquakes permanently alter the shape of the Earth. The crust bends, stretches, compresses, rises, and sinks. Entire landscapes can be transformed in less than a minute. During a large thrust earthquake, the overriding plate behaves somewhat like a compressed spring. For years, tectonic forces slowly deform the crust. When the fault finally ruptures, the crust rebounds toward a new position. Geologists refer to this process as elastic rebound. The resulting movement can raise certain areas while lowering others. The June 8 earthquake appears to have produced substantial uplift across portions of the southern Mindanao coastal zone. Reports emerging in the days after the earthquake described reefs exposed above the waterline, altered tidal patterns, unusual shoreline positions, and dramatic changes in local coastal geography. Locations that had previously been covered by shallow seawater became exposed land. The phenomenon is known as co-seismic coastal uplift. The term may sound technical, but its meaning is straightforward. Co means together. Seismic refers to the earthquake. The uplift occurred during the earthquake itself. Unlike erosion, sediment accumulation, or long-term geological change, this transformation happened almost instantly. The effect can be astonishing. Imagine a gently sloping coastal shelf extending hundreds of feet offshore. If that shelf suddenly rises by approximately 6.5 feet or 2 meters, the shoreline may shift dramatically seaward. Water that once covered the seabed can no longer reach its former extent. Areas that had always appeared submerged become permanently exposed. To observers on the coast, the result may appear almost impossible. The ocean seems to disappear. In reality, the water has not gone anywhere. The land has moved upward. Along shallow coastlines, even a relatively modest vertical uplift can produce large horizontal shoreline changes. If the seafloor slopes gradually, a rise of only a few feet may expose hundreds of feet of previously submerged terrain. Coral communities, tidal flats, seagrass beds, and shallow lagoons can suddenly find themselves above normal sea level. This appears consistent with reports from affected areas following the earthquake. The newly exposed coastal zones represent visible evidence of one of Earth's most powerful geological processes. They serve as a reminder that coastlines are not fixed boundaries. They are temporary expressions of an ongoing contest between tectonic forces and sea level. Historical examples demonstrate just how dramatic such transformations can become. In Alaska, during the Great Earthquake of 1964, some coastal regions rose by more than 30 feet, or approximately 9 meters. Elsewhere, neighboring areas sank. Entire ecosystems were transformed. Forests that had stood above sea level became flooded. Other coastal regions expanded outward as uplift exposed new land. The 2011 Tohoku earthquake in Japan produced widespread coastal deformation. Sections of the coastline experienced vertical movement that permanently altered local geography. Ports, seawalls, harbors, and fishing grounds all had to adapt to the changed landscape. The geological mechanisms operating during those events are fundamentally similar to those associated with the June 8 earthquake in southern Mindanao. Large thrust earthquakes are capable of lifting entire coastal regions because the fault rupture extends across enormous areas beneath the Earth's surface. The magnitude 7.8 event released an extraordinary amount of energy. Compared to a magnitude 6 earthquake, it released hundreds of times more energy. The scale of deformation associated with such an event extends far beyond the immediate vicinity of the epicenter. Even though the earthquake occurred offshore, its effects propagated throughout the crust. One of the most intriguing developments reported after the earthquake involved the appearance of sinkholes and localized ground subsidence in parts of Balut Island and several coastal areas of southern Mindanao. At first glance, uplift and subsidence might seem contradictory, yet both phenomena commonly occur during major earthquakes. The Earth's crust rarely moves as a single rigid block. Different sections respond differently to stress release. Some regions rise, others sink, still others undergo lateral movement. The emergence of sinkholes after a major earthquake often reflects changes in underground conditions. Strong shaking can destabilize subsurface materials. Fractures may open, sediments can compact, groundwater pathways may shift. Cavities that were previously stable can collapse. The same earthquake that raises one stretch of coastline may simultaneously trigger localized subsidence nearby. Such patterns are not unusual following major tectonic events. Ground failure models, generated shortly after the earthquake, indicated significant potential for both landslides and liquefaction across affected areas. Extensive population exposure to these hazards was also identified. Liquefaction deserves particular attention because it represents one of the most remarkable consequences of intense shaking. When water-saturated sediments are subjected to strong seismic vibrations, they can temporarily lose strength and behave almost like a liquid. Buildings tilt, roads deform, ground surfaces crack and settle. In coastal regions, liquefaction can dramatically alter local topography. Combined with tectonic uplift and subsidence, these effects can create a highly complex post-earthquake landscape. The environmental consequences extend well beyond geology. Coastal ecosystems are extraordinarily sensitive to changes in elevation. Coral reefs, for example, occupy narrow depth ranges where sunlight, water movement, and temperature conditions remain favorable. If an earthquake suddenly lifts a reef above sea level, many organisms may be exposed to conditions they cannot survive. Intertidal habitats experience similar disruptions. Species adapted to periodic tidal flooding may suddenly find themselves permanently above the reach of normal tides. Conversely, subsiding areas may become submerged more frequently than before. Mangrove forests, seagrass meadows, shellfish habitats, and coastal wetlands can all be affected by abrupt tectonic deformation. These ecological adjustments may continue for years. At the same time, new habitats may emerge. Newly exposed coastal platforms can become colonized by different organisms. Sediment transport patterns may shift. Fresh channels may develop. Shoreline processes begin responding immediately to the altered topography. The earthquake therefore marks not only a geological event, but also the beginning of a long period of environmental adjustment. One of the most common questions arising after reports of coastal uplift is whether the ocean will eventually return to its former position. In most cases, the answer is no. When a major thrust earthquake permanently lifts part of the crust, the change generally remains. The Earth's surface has been reconfigured. Tides will continue to rise and fall. Storm surges may temporarily flood newly exposed areas. Seasonal weather patterns may alter the appearance of the shoreline. Waves and currents will gradually redistribute sediments. Yet these processes do not reverse the tectonic displacement itself. The land remains higher. Only another significant tectonic event producing opposite motion could potentially return the area to its previous elevation. Even then, such changes would likely occur over decades, centuries, or longer. For practical purposes, the coastline created by the earthquake becomes the new coastline. This reality has important implications for communities that depend on coastal resources. Fishing grounds may shift. Boat access points may require modification. Harbors and small landing areas may experience changes in water depth. Traditional navigation routes may need adjustment. Aquaculture operations may encounter altered environmental conditions. Infrastructure designed around the former shoreline may suddenly find itself disconnected from the water. Throughout history, coastal populations living near subduction zones have repeatedly faced these challenges. The Earth is not static. The shorelines visible on maps represent only temporary snapshots within a constantly evolving geological system. Another striking aspect of the June 8th earthquake is its depth and tectonic setting. Although the event's reported depth was approximately 34 miles or 55 kilometers, the preferred moment tensor solution suggested rupture characteristics associated with deformation occurring within the broader subduction environment. This distinction matters because it highlights the complexity of tectonics around Mindanao. The southern Philippines sits at the intersection of multiple active structures. Rather than a single fault controlling all seismic activity, the region contains numerous interacting systems. Stress can be transferred between faults. Ruptures can influence neighboring structures. Earthquakes may occur within the subducting plate, along the plate boundary, or within the overriding crust. The resulting seismic behavior can be exceptionally complex. Yet despite this complexity, the evidence consistently points toward a powerful compressional event capable of generating substantial vertical deformation. That deformation remains one of the defining features of the earthquake. The shaking itself has already passed into history. The uplift remains visible. Future geological surveys will likely provide increasingly detailed measurements of how much the land moved. Satellite observations, drone mapping, field investigations, and shoreline analyses may reveal variations in uplift from one location to another. Some stretches of coast may have risen only modestly, others may have experienced significantly greater displacement. Precise measurements require time, careful mapping, and extensive verification. Even without those final datasets, the broad picture is already clear. A major thrust earthquake struck the southern Philippines. The rupture lifted portions of the coast. The shoreline shifted, marine environments were exposed. Ground deformation extended across multiple areas. Sinkholes and subsidence appeared in some locations. The landscape changed. Events like this provide rare opportunities to observe geological processes that usually unfold over immense timescales. Mountains, coastlines, islands, and ocean basins are often thought of as permanent features. In reality, they are products of continuous tectonic activity operating over millions of years. Most of the time, those changes occur too slowly for people to notice. Occasionally, however, the planet compresses centuries of geological change into less than a minute. June 8, 2026 was one of those moments. At 7:37 in the morning, the crust beneath southern Mindanao shifted with extraordinary force. A magnitude 7.8 earthquake released accumulated tectonic stress and permanently altered part of the Philippine coastline. Land rose. Shallow seafloor emerged. Coastal geography changed before the eyes of those living nearby. The event demonstrated one of the most powerful realities of Earth science. Coastlines are not fixed edges of the continents, but moving boundaries shaped by the relentless motion of tectonic plates. Long after aftershocks fade and damaged structures are repaired, one consequence will remain visible. Along portions of southern Mindanao, the shoreline now occupies a different position than it did before that June morning. The sea did not retreat by choice. The land itself rose to meet the sky, leaving parts of the former seafloor exposed as lasting evidence of a monster earthquake that lifted the coast by 2 meters and changed the map forever. Perhaps the most remarkable aspect of the coastal uplift is that it offers a rare glimpse into a process that normally remains hidden beneath thousands of feet of ocean water. Along most subduction zones around the world, similar deformation occurs offshore and escapes direct observation. Instruments detect it, satellites measure it, and scientists analyze it, but ordinary people rarely witness the physical evidence with their own eyes. Southern Mindanao became an exception. The newly exposed coastal platforms effectively revealed a section of the geological machinery responsible for building islands and shaping continents. Every major mountain range on Earth ultimately owes its existence to similar tectonic forces. Compression, uplift, faulting, and crustal deformation have sculpted landscapes throughout geological history. The difference is usually one of timescale. Mountain building commonly unfolds across millions of years. Coastal uplift associated with a major earthquake can occur in less than a minute. That contrast makes events like the June 8 earthquake particularly significant. The same forces that gradually create entire landforms acted here with unusual speed, allowing the results to become immediately visible. Satellite observations conducted after large earthquakes often reveal deformation patterns extending across hundreds of square miles. In many cases, the crust behaves almost like a flexible sheet. Some portions arch upward, while neighboring areas bend downward. The resulting pattern resembles a massive geological ripple frozen into the landscape. The uplift reported along portions of the southern Mindanao coast likely represents only one component of a broader deformation field produced by the rupture. Elsewhere, movements may have been smaller and therefore less obvious. A rise of only several inches might escape notice without precise surveying equipment. Yet even minor changes can influence drainage systems, groundwater flow, coastal erosion, and ecosystem dynamics. The cumulative effect demonstrates that earthquakes are not isolated points of shaking. They are regional geological events capable of altering vast areas simultaneously. Another important consequence involves tidal behavior. When coastal land rises, local tidal patterns can appear different, even though the tides themselves remain unchanged. Areas that previously flooded during high tide may remain dry. Channels once navigable throughout the tidal cycle may become shallower. Small coves and inlets may experience altered circulation patterns. Residents familiar with generations of local coastal conditions often notice these changes immediately because the relationship between land and water has shifted. This phenomenon helps explain reports that sea levels in some affected areas appeared abnormal days after the earthquake. The ocean was continuing its normal tidal rhythm. The coastline against which those tides operated was no longer the same. Changes of only a few feet can have surprisingly large impacts in shallow environments. A difference of approximately 6½ feet, or 2 meters, can transform the appearance of entire stretches of shoreline. Rocks previously hidden beneath the water become permanent features of the landscape. Sandbars may emerge where none existed before. Formerly submerged coral formations can become visible from shore. For communities accustomed to a particular coastal setting, the transformation can feel as though the geography itself has been rewritten. In reality, that is exactly what occurred. The event also serves as a reminder that the Philippine archipelago remains a product of ongoing tectonic activity. The islands are not static landmasses resting quietly in the ocean. They are active geological features located along one of the most dynamic plate boundary systems on the planet. Volcanoes, earthquakes, uplift, subsidence, and fault movements are all expressions of the same fundamental process, the continuous motion of tectonic plates. Over millions of years, these forces have assembled the modern Philippines piece by piece. Portions of crust have collided, rotated, fractured, risen, and migrated. Ancient volcanic arcs have merged with other blocks of crust. New faults have formed while older ones became inactive. The landscape visible today represents only the latest stage in that evolution. Future earthquakes will continue the process. Some coastlines may rise further. Others may sink. New land may emerge while existing features are modified or removed. The June 8th earthquake therefore belongs within a much larger geological continuum, stretching far beyond human history. Long before written records existed, similar earthquakes were reshaping the region. Long after the present generation is gone, tectonic forces will continue altering the boundaries between land and sea. Evidence of those ancient events can still be found throughout the Pacific region. Elevated coral terraces hundreds of feet above modern sea level reveal former shorelines lifted by repeated earthquakes over thousands of years. Marine fossils preserved inland mark locations that were once submerged beneath the ocean. Coastal cliffs record cycles of uplift and erosion, extending back through countless generations of seismic activity. The newly exposed coastal zones of southern Mindanao may eventually become part of that geological archive. Years from now, the uplifted reefs and altered shorelines could serve as permanent markers of the June 2026 earthquake. Future researchers may study them to reconstruct the exact pattern of deformation produced by the rupture.